Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're going to talk about the chess ELO rating system. There are a number of videos you can find on the chess ELO rating system, but none that explain it with the details I'm about to give you to my liking. At least none that I could easily find. A lot of the videos out there will actually ignore a lot of the key mathematical concepts or try to focus on normal distribution stuff that has nothing to do with the important aspects of the ELO rating system. And I figured I'd make a video that actually describes the thought process behind the ELO formulas, explaining the logic behind why they are what they are. As you probably know, or hopefully as you know, with the chess ELO rating system, or a lot of other games using ELO rating system, where each player will have some rating, and if you get better, your rating is going to go up. If you get worse, your rating will go down. And the way that's done is if you play games against other people, if you start winning those games, your rating goes up. If you start losing those games, your rating goes down. And your rating should stabilize around your true rating. Obviously, there's going to be some statistical noise, but it should be a pretty good approximation of your true rating. And the key to the rating system is figuring out if you win, how many points do you gain? If you lose, how many points do you lose? If you draw, if you were higher rated than your opponent but you drew, you should lose a few points. If you're lower rated than your opponent but you draw, you should gain a few points. And the question is, how many are we talking about? And I'll first describe the math for what happens if you're playing a game where draws are impossible, where every game has one winner and one loser. And then if draws are a thing, I'll show how to modify everything off of that. It's easier to describe it in the simple win-loss case and then go from that to draws than trying to handle all that at once. So in a simple win-loss case, in order for any rating system to actually be meaningful, or for your rating to mean what you want it to mean, for it to actually be a reflection of your strength, then that rating system must follow what's called the Martingale property. Martingale property states that for repeated matchups between the same pair of players, assuming both players are appropriately rated, neither player will tend to gain or lose points. So, for example, what this would mean is that if you were playing against a series of weaker opponents than you, on average, if you, let's say, played 100 games against players weaker than you, and suppose you weren't actually improving at the game through playing, so your true strength was the same before and after, on average, your rating should be the same after those 100 games as it was before. Or suppose you were playing a bunch of games against a player stronger than you. Again, your rating should be the same after those 100 games as before. 100 just being a number I'm picking just to show the concept of repeated matchups. To look at this from a single matchup, what you'd say is, given that you have some probability of beating some other player, you have to figure out how many points you would gain or how many points you would lose based on winning or losing the game. So suppose you're at some rating, and you're playing somebody, and suppose you have, let's say, a 60% chance of beating that person. You'd say probability of a win equals 0.60. Yeah, generally mathematicians don't tend to write out probabilities as percentages. We'll write that, so percentages are numbers ranging from 0 to 100. We'll just divide everything by 100 and write probabilities as numbers between 0 and 1. So probability of a loss, in this case, would be 0.4. And you want to figure out the number of points that you'd gain or lose. So you'd gain some number of points if you won, you'd lose some number of points if you lost. And so let's assume that X is the number of points that you gain if you win, and Y is the number of points that you lose if you lose. So now if we were to look at the average number of points that you would gain, let's say, okay, so we would say, if we look at the number of points that you would gain, that would be, you would gain positive X with a probability of 0.6, and you'd lose negative Y with a probability of 0.4. And we're saying that on average, your ending rating after the game should be the same as your rating was before the game. This means that your number of points gained, we're counting lost points as negative gains, your number of points gained on average should be 0. And so your thought might be, okay, I look at these two numbers, x and negative y, and I take the average, and you might think, I'll put this in red because it's wrong, you might think that you want to say x plus negative y divided by 2. Hey, look, I'm averaging these two numbers, should be 0, multiply by 2, x plus negative y equals 0, add the y to both sides, x equals y. But it doesn't work that way. Because when I say on average in the long run, remember, this probability, or this win will happen more often than this loss. When we take a probabilistic average, we need to take a weighted average using these probabilities as the weights. So we have to bear in mind that this x is actually happening 60% of the time, and this negative y is happening 40% of the time. The one case where a lot of students are probably used to seeing a weighted average is for calculating grade point averages, right? If you've got different exams worth different amounts, you realize, oh, I have to count that and multiply that by however much it's worth. So these probabilities are how much it's worth. So you would actually say x times 0.6 plus negative y times 0.4 divided by the total sum of the weights for probabilities that should consistently be 1, but we'll say 0.6 plus 0.4, which sure enough is equal to a 1. Okay, that has to be 0. And doing the algebra, that'll get us x times 0.6 minus y times 0.4 equals 0. 0.6x equals 0.4y. And while we can't solve for x and y directly, we can get the ratio of x divided by y. And equal 0.4 divided by 0.6. In other words, you just look at the probability of the opposite happening. Your points gained or lost will be proportional to that opposite probability. So you have to pick some starting number for how many total points at stake will you be looking at. Right? Notice that the difference between the points gained for a win and points gained for a loss, remember that points gained for a loss is negative, right? So the difference between these is going to be x plus y, right? You're comparing x to negative y, so you subtract one from the other, you get x plus y. X minus negative y will get you x plus y, right? So you pick some, suppose that number was 10 for argument's sake. Right? So you have x plus y must equal 10, you need this ratio, you'll get, oh, x must be 4 and y must be 6, right? X is going to be 0.4, right? This opposite probability, 0.4 times the number of points at stake. Y will be 0.6 times the number of points at stake. For example, on chess.com, once you've been playing for long enough without taking that many extended breaks, so that you're at a standard ELO system. Chess.com uses a slight variant of that, but they call it the Glicko system rather than the ELO system. Let's focus on just the ELO system here. Once you've been playing for long enough so that you're effectively using the ELO system, their number is 16 per game. So that for two evenly matched players, you gain 8 points for a win, lose 8 points for a loss. If you were going up against somebody and it was estimated that you had a 3/4 chance of winning, then you would only get 4 points for a win and 12 points for a loss. Right? We'll worry about draws later. That'll be at the end. But that's the first idea of you need to establish this martingale property where just playing a game would not, on average, raise or lower your ELO. It would have a neutral effect on average. But then the remaining question is, how do we relate these differences in ELO to a win probability, right? Well, we know that this probability, right, getting these probabilities here, right? Well, okay, we kind of get it. That's going to depend on whether you are higher or lower rated than your opponent. If you're higher rated, this win probability will be higher. If you're lower rated, this loss probability will be higher. But how would we figure that out? The main idea behind the ELO rating system is how it answers the question about differences in players' ratings leading to these win rates, or these estimated probabilities of winning or losing. So the first main step in figuring out how to go from a difference in ELO ratings to a win rate is you have to identify what I'm going to call the challenge factor. We'll let the letter C represent the challenge factor. And we define the challenge factor as C equals, if P is your probability of winning, then the challenge factor is equal to your probability of losing divided by your probability of winning. In general, the greater your probability of losing is, and thus the lower your probability of winning is, the higher the challenge factor. Some special cases to look at: if your probability of winning is exactly 50%, then your challenge rating, right, would be 0.5, right? 1 minus 0.5 is also 0.5, right? 1 minus 0.5 divided by 0.5. So your challenge rating would be 1. If you had a 2/3 chance of winning, then you only have a 1/3 chance of losing divided by 2/3 chance of winning. 1/3 divided by 2/3 is 1/2. Your challenge rating would only be a half. If you had a 3/4 chance of losing, right, so only a 1/4 chance of winning, you have lose probability of 3/4, win probability of 1/4, your challenge factor would be 3. So if you are guaranteed to win, your challenge factor would be 0. And if you're guaranteed to lose, your challenge factor would be infinite. An impossible task could be considered infinitely challenging. And again, something that you have a 50-50 shot of succeeding on, challenge factor is just 1. We consider that pretty neutral. Right? Numbers bigger than 1 mean you're up against a tougher opponent. Numbers lower than 1 mean you're up against a weaker opponent. All right? Fine. So why is this challenge factor important? So suppose we ask the question, well, how would challenge factors relate to each other if different players were to play against each other? So as an example, suppose I'm just starting whatever game this is, and you've been playing for a really long time, and we both know somebody who's somewhere in between our strengths, right? So suppose I'm an absolute novice. My challenge factor against that other player is, let's say, a 3. If I play this person, I only have a 25% chance of winning. And if that other player struggles a bit, but not quite as much against you, that other player will win only 1/3 of the time against you. So now, if you and I were to face off against each other, what would my challenge factor be against you? And ELO's assumption is you multiply the challenge factors, right? And if you chain that into a whole bunch of other people, right? If I say, okay, mine versus another player, player versus someone we've barely even heard of, that player we've barely even heard of against you, you just multiply as long as you're going in the right order. So we'd say in this case, challenge factor would equal 6 in this case. Okay, so however it is that we handle this way of comparing ratings to win probabilities, it needs to follow this rule. It needs to follow this multiplying of challenge factor rules. So the last piece we need is some initial scale factor, some way of indicating just something about difference in points somehow leading to a challenge factor, and the decision that Arpad Elo made when he was coming up with his system to begin with was he just said, let's make a 400-point deficit lead to a challenge factor of 10. It's a somewhat arbitrary choice, but the way the chess system works, that's just the one they went with. Any other system would have been just as good. Okay, so that should mean a 400-point deficit should be a challenge factor of 10, and 800-point deficit would be a challenge factor of 100. A 200-point deficit should be a challenge factor of, it's going to have to be the square root of 10, right? So that if I compare two people. Suppose someone's rated 1200, someone else is rated 1400. Okay, that's going to be challenge factor square root of 10. Then you compare 1400, 1600. If that's also a square root of 10, then when you compare the 1200 to the 1600, now that gets you a challenge factor of 10 like you're supposed to, which you would get by multiplying those two square roots of 10. All right, next we're going to need a formula that just gets you challenge factor as a function of the difference in rating points. Some algebraic function. Now, if you're thinking, well, okay, every time I add two things together, I'm adding together two differences in ratings, that turns into multiplication by 10, or by 10 to whatever I need, right? Just some sort of multiplication. The operation that allows you to do that is exponents, as long as your differences in ratings are inside the exponent. So that just gets us the formula. The challenge factor will be 10 to the power of your rating minus your opponent's rating all over 400. The division by 400 is still in the exponent. So the next piece is how to convert from a challenge rating to a win probability. Let's just put our formula for the challenge rating over here, right? We said 10 to the power of your rating minus opponent's rating over 400. But we also have that formula that challenge rating equals loss probability divided by win probability. Now we want to isolate win probability by itself. And here's how we do that. We multiply both sides by the win probability to get a linear equation. We now want to isolate for our unknown p, right? We're going to assume that we know the challenge rating already. So we add the win probability to both sides. Factor out our win probability by combining like terms. And we get our win probability equals 1 over 1 plus our challenge rating. That's just going to equal 1 over 1 plus 10 to the power of your rating minus the opponent's rating over 400. All right, so the final piece becomes finding the number of points at stake per game. That is actually going to depend on each game. So the final piece is going to be finding the number of points at stake per game. That's actually going to depend on which game you are playing. It's going to depend on whether or not it's easier to actually be that much better than another player. And then it's also going to depend on how easy it is for a person to actually improve over the course of time, right? So with all that in there, what you'd actually do is you wouldn't start thinking about it theoretically. You'd probably just do it observationally, of just looking at players playing each other over the course of time. And so let's think about what would happen if the number of points at stake per game that you chose was too small or too big. Suppose the number of points at stake were too small. That would mean if you've been playing for a while and you actually start getting better, the rating system wouldn't be giving you as many points as you necessarily deserve. And so if you actually got better and were winning 60% of the time when the system would think that you'd only win 50% of the time. So your rating will start going up, but if you pick too few points at stake per game, it's going up too slowly. Which means if you start gaining a bunch of points, it probably means you got better, and it probably means you're underrated, because such a system would underrate true improvements. Now, notice, it could also be that you're just getting lucky. But if you really were getting better, the system would be underrating you. And so, suppose that you're in a situation where your rating is noticeably higher than it was 20 games ago. if the number of points at stake were too low, you would expect that the system is still underrating you, though maybe not quite by as much, because you have started to gain some points. And so if you gained a bunch of points over your past 20 games, you would expect to continue to gain. Or, I suppose, if you got worse, right, if suddenly you I don't know, for whatever reason you're getting worse, then if your rating went down over the past 20 games, you'd expect it to go down over the next 20 games. In contrast, suppose that the number of points at stake were too large. If you start winning a bunch of games, it's going to give you too many points. And so, yeah, it's recognizing that you're better, but it's going to overdo it. And so, facing off against a player that you should have a 60% win rate against, maybe the system will think you have a 70% win rate, and thus not give you enough points for a win, and give you too few points for a loss. Now, you might ask, well, wait, how could it overshoot like that? Maybe you just had a lucky winning streak. But either way, if your value is too big, now if you had players that were gaining points over their past 20 games, you would expect them to lose points. So what you can do is you can try different numbers and check for those correlations. And once you find a number that those correlations don't really happen, right? Gaining points over 20 games doesn't lead to continuing to gain or continuing to lose. It's like, over those 20 games, yeah, we think that that's around where you are now. Right? You adjust your rating appropriately. Once you have that, then you found the right number. Okay. And so this suppose that number is K, right? Let K represent the number of points at stake per game. Then, if you remember, number of points for a win was K times your loss probability. Number of points for a loss will be K times your win probability. Your win probability is this much. So, if you're assuming X points for a win and Y points for a loss, so X, the number of points you gain for a win, will be K times your loss probability. That's 1 minus your win probability. And Y, the number of points for a loss, will be K times your win probability. So these are the formulas you're likely to see from other math YouTubers. Okay. Finally, let's deal with draws, right? How draws will work. And all you do is you consider a draw to be like half a win and half a loss. So rather than saying that your P rating here, what I'll call modified, so rather than saying your win probability is just P, probability of a win, if I say your modified win rate, I'll say this P will equal probability of a win plus half a probability of a draw. And then everything else is the same. You still have that your challenge rating is now 1 minus P divided by P. Your number of points for a win is this much. Your number of points lost for a loss is just this much. How many points for a draw? Well, if a draw is like half a win and half a loss, let's say Z will be number of points for a draw. Z is just going to be half of X. Remember, you lose points for a loss, so we'll say minus half of Y. So we can factor out a K here. We'll say K times, well, K times 1/2 of each, so I guess we can say K over 2. Times, we'd say 1 minus this here. Remember, with this K out here, the negatives are going to cancel, so we'll say 1 minus 2 over 1 plus 10 to the power of Ry minus our opponent over 400. And that's the basic rundown of the ELO system. I hope you found this useful. And if you want to arrange private lessons, click the link in the description below. And as always, this is Dr. Nighttime wishing you a good night.